Divisibility rules for 2 through 10 per request. I made a PDF and I'll put that in the description, but here is just a very pausable version of descriptions that can go along with that. Now I'm not going to put them in order 2, 3, 4, 5. I'm going to put them in groupings that I think are logical, like 2 to the something power should all go together. So 2, 4, and 8 are all going to be in one group, and 3 to the something power should all be in one group. So 3 and 9. Things that are composite numbers are going to be in one group, and stuff that doesn't really have another something to go with, those are going to be in a last group. Powers of 2 go together. 2 to the first power, we look at the last single digit. For 2 to the second power, which is 4, we look at the last 2 digits. For 2 to the third power, we look at the last 3 digits. So whatever kind of power of 2 it is, that's how many digits we have to look at the end. For 934, it ends with a 4. That's even. So it is, in fact, divisible by 2. 72 ends with a 2, and that's divisible by 2. That's even. So the whole thing is divisible by 2. 841 ends with a 1. That's an odd number, and therefore the whole thing is not divisible by 2. 2,348. It ends with a 48, and the 48 is divisible by 4, which means that the whole number 2,348 is also divisible by 4. It doesn't matter how big the rest of it is. It's just the last 2 digits. Are those 2 digits together divisible by 4? For 156, well, 56 is divisible by 4 because 56 is divisible by 8, so therefore it must be also divisible by 4. For 4,231, 31 is not divisible by 4, so therefore the whole thing is not divisible by 4. And 1,734, even though 34 is even, and even though it ends with the number 4, I have to look at the 34. 34 is not divisible by 4, so therefore 1,734 is not divisible by 4. 720,648. I only look at the last 3 digits to check divisibility by 8. And I see a 64 and an 8, so 648 is in fact divisible by 8, but it requires knowing your 8 times tables all the way through 3 digits, and really who cares at that point? It's kind of fun to know what the rule is, but nobody really cares, and nobody's actually using this rule. A lot of people use the 4 rule or something like that, and then maybe use a 2 again, but it does work because it's based on powers of 2. This is the third power of 2, so I have to look at the last 3 digits. For powers of 3, that's 3 to the first power and 3 to the second power, that's 9, so 3 and 9. Then I add up all of the digits and I check the sum. Is that sum divisible by that number? Check divisibility by 3. For 345, check 3 plus 4 plus 5. 3 plus 4 plus 5 is 12. Can you divide 12 by 3? Of course you can, so therefore you can also divide 345 by 3. 1,002. Add up 1 plus 0 plus 0 plus 2. That's 3. Can you divide 3 by 3? Yes. That means that you can also divide 1,002 by 3. 421. If you add up those digits, 4 plus 2 plus 1 is 7. So even though the end of it is 21, we don't care. We're only checking the sum of the digits. And the sum of the digits is not divisible by 3, which means that the whole thing is not divisible by 3. Divisibility by 9 is the same rule, and this one makes sense too, because if you've ever multiplied something by 9, let's say 9 times 3, you put down your 3rd finger, 9 times 5, you put down your 5th finger. If you have 10 fingers and you're always putting down 1, shouldn't the sum of all the fingers left over be 9? This doesn't only work for 2-digit numbers, but it works for any set of digits. So if I want to check to see if 27 is divisible by 9, 2 plus 7 equals 9, therefore 27 must be also. But it works for bigger things. So 117, 1 plus 1 plus 7 is also 9. Which means that I can divide 117 also by 9 because the sum of the digits is 9. For 9,203,841, I add up 9 plus 2 plus 0 plus 3 plus 8 plus 4 plus 1, and I get 27. Can you divide 27 by 9? Yes, you can, as previously mentioned. So you can also divide 9,203,841 by 9. 5 and 7 are going to be isolated, kind of these one-off kind of rules, because we're only looking at divisibility rules from 2 to 10, and none of the powers of either of those numbers are going to be on the list beyond, the first power, other than the number itself. They're prime, they're not composite, so we're just going to have, here's the rule, and then we move on. You can see divisibility by 5 if the last digit is either a 5 or a 0, like 35 or 80, or that big number that I don't want to read, or the other big number that I don't want to read. But they end in either a 0 or a 5, so we know that it's divisible by 5. 7's kind of a weird rule because we're going to cross off the last digit and then subtract double of whatever we just crossed off. So if I cross off the last digit 8 and subtract 16 from what's left over, I get 21. Since you can divide 21 by 7, you can divide 378 by 7. Likewise, if I want to check divisibility of 455 by 7, then I cross off the last digit, which is a 5. I subtract 10 from what's left over because it's double 5. 45 minus 10 is 35. If I can divide 35 by 7, then I can divide 455 by 7 also. A composite number is just a product of two other things, and so 6 and 10 are both made up of factors that are already on the list. So if you want to check divisibility for 6, you check the rule for 2, and then you check the rule for 3. If they both work, it must also be divisible by 6 because of multiplication. Same thing goes for 10. You check the rules for 2 and 5, but the only time that that's true is if it ends with a 0. So we're just going to say that the rule for 10 is that it ends with a 0 because that's already combining the rule for 2 and the rule for 5. That's the intersection of the stuff that's divisible by 2 and divisible by 5. Checking to see if 522 is divisible by 6, I'm going to check the rule for 2. Is the last digit even? Yes, it is. It's a 2. It's even. And then I'm going to check to see if it's divisible by 3. 5 plus 2 plus 2 is 9, and 9 is divisible by 3, which means that 522 is divisible by 3. Well, if 522 is divisible by both 2 and 3, it must also be divisible by 6. And it doesn't matter how big and nonsensical the number is. This is not really nonsense. It's just a big number, and I don't feel like reading it. But it ends with a 0, which means it is divisible by 10. Even though it's not really on our list, you could extend this divisibility by saying something like, you can check divisibility for 12 by checking the rule for 3 and the rule for 4, because 3 and 4 have no overlapping factors, and they work independently of each other, so you can just go ahead and use those two. You couldn't use, let's say, 6 and 2, because those have overlapping factors in them. But if you check to see if something's divisible by 3 and divisible by 4, well, you pretty much already checked to see if it's divisible by 12. Same thing would work with, let's say, 15. If the rule for 3 works and the rule for 5 works, then it must be also divisible by 15. Now here's some bonus content. If you want to know why the 2 to the n works, then it's based on the idea of tens and hundreds and thousands. So if I want to check divisibility by 2, I know that anything times 10 is automatically divisible by 2. So I'm just going to check the last digit because everything other than the last digit is some sort of multiple of 10, which is divisible by 2. If I want to check divisibility by 4, I only have to check the last 2 digits because everything except for the last 2 digits is a multiple of 100, which is automatically divisible by 4. If I want to check for divisibility by 8, I check the last 3 digits because everything else is going to be a multiple of 1,000, which is automatically divisible by 8. A very abbreviated conversation of why the 3 to the n stuff works. Let's take a look at something that's divisible by 9, 2,198. Write it in expanded form, then it's 2,000 plus 100 plus 90 plus 8, which is the same thing as 2 times some sort of power of 10, 1,000, plus 1 times another power of 10, which is 100, plus 9 times a power of 10, plus 8. Well, all those powers of 10 are 1 away from a bunch of stuff that's 9s. So 2 times, instead of 1,000, it's 999 plus 1 times 99 plus 1, plus 9 plus 9 plus 1, plus 8 times just a regular 1. Well, we already know that 999 and 99 and 9 are divisible by 9, so let's just get rid of those. That's just the sum of the digits now. And the reason that divisibility by 7 works is because what we're really doing is subtracting off chunks of things that are multiples of 21, which we already know is divisible by 7, so we just look at what's left over.